Welcome back to Chapter 4 of our video course on the AI in marketing. In this module overview we will cover the topics like: what are AI algorithms and how they work? What are the various types of commonly used AI algorithms under the different kinds of learning patterns like supervised, unsupervised and reinforcement learning? A brief on Algorithmic Bill of Rights. Let's start with introduction to AI algorithm. So, what is an algorithm? An algorithm is a set of step-by-step instructions that tell a computer how to perform a task or calculation. AI algorithms are special programs that allow machines to learn and operate on their own. The regular algorithms can be simple while AI algorithms are more complex. They work by taking in training data and using that information to learn and improve over time. The way this training data is collected and labeled is what differentiates the major types of AI algorithms. At its core, an AI algorithm intakes training data, either labeled by humans or unlabeled, and uses that data as a basis to learn how to complete its assigned tasks. Some algorithms can even continue learning and refining themselves with new data. There are three main categories of AI algorithms as we have already learned in the previous chapters, and they are: 1. Supervised learning. These algorithms learn from data that is clearly labeled by humans. It's like a student learning in the presence of a teacher providing the correct answers. Supervised learning predicts outcomes based on the labeled training examples. 2. Unsupervised learning. These algorithms learn from unlabeled data by finding patterns and similarities on their own, without any guidance. It automatically groups and clusters the data. 3. Reinforcement learning. These algorithms learn by trial and error using feedback from actions taken in an environment. It learns which actions yield the best results or rewards over many iterations. The key is that AI algorithms, unlike traditional programs, are designed to automatically learn and improve from data, with little to no human intervention required after the initial training process. Within these categories, there are many specific AI algorithms used for different tasks. We'll discuss some of the most popular and widely used ones. We will start with decision tree. A decision tree is a type of supervised learning algorithm that works by breaking down data into smaller subsets based on certain decision rules or conditions. It gets its name from the way it represents decisions visually, as a upside-down tree structure. The root at the top represents the entire dataset. This branches into nodes, which are conditions/attributes to test. Each node leads to further sub-nodes or leaves, which are the final decisions/classifications. So the tree starts from the root and follows the branches based on asking a series of true/false questions about the data's attributes, until it reaches a leaf node, which is the prediction/decision. The algorithm learns these decision rules by analyzing patterns in historical training data that was labeled with the correct classifications already. Some key advantages of decision trees are: they are simple to understand and interpret. They can handle both numerical and categorical data. They require little data preparation. Decision trees are commonly used for tasks like data mining, decision analysis, and pattern recognition across many industries like finance, marketing, and healthcare. The core idea is to break down a complex decision into a series of simpler decisions that lead to a final conclusion, represented visually as branches on a tree. Next, we will discuss about random forest. A random forest is a collaborative learning algorithm that combines multiple decision trees to improve accuracy and prevent overfitting. Instead of relying on just one decision tree model, it creates a forest of many decision trees during training. Each individual tree gives a prediction classification, and the random forest chooses the final prediction by either averaging the numerical outputs from each tree, for regression problems, or taking the majority vote among the classification categories. The random part comes from the way each tree is built, by using a random subset of features from the training data rather than the full feature set. This randomness introduces diversity among the trees, allowing the forest to capture a wider range of perspectives on the data. Combining many random trees helps cancel out their individual biases or errors. Some of the key advantages of random forests are that it is highly accurate due to the ensemble learning approach. Handles high-dimensional and missing data well. Prevents overfitting by averaging multiple uncorrelated trees. Can estimate feature importances easily. Random forests are versatile and used across many domains like recommendation engines, image classification, finance, and healthcare for tasks like predictions, outlier detection, and feature selection. The core concept is that by combining many randomized decisions tree models, we get a robust, accurate, and reliable predictive model. Now we will discuss about support vector machines. SVM is a powerful supervised learning algorithm commonly used for classification problems, although it can also handle regression tasks. The core idea behind SVM is to find the optimal separating line or hyperplane that segregates or differentiates the different classes of data points in the best possible way. It does this by first plotting each data point onto an n-dimensional space, where n is the number of features or data points. There can potentially be multiple hyperplanes that separate the classes. However, SVM aims to select the hyperplane with the maximum possible margin between the nearest data points of each class. These nearest points are called the support vectors. Maximizing this margin distance provides the biggest buffer or gap between the classes, reducing the risk of misclassification errors on new data points. The visuals shown below illustrate this well. The black hyperplane correctly separates the two classes while also maximizing the margin from the support vectors. The blue and orange lines, while separating the classes, do not maximize the margin, increasing classification errors. So SVM focuses on selecting the hyperplane that gives the widest possible separation gap from the most difficult to classify instances, support vectors, in the training data. This margin maximization principle is what allows SVM to have good generalization performance on unseen data, beyond just maximizing training dataset accuracy. The next topic is naive Bayes. The naive Bayes is a popular supervised learning algorithm used for classification problems. It calculates the probability of an instance belonging to each class, based on the feature values present in that instance. It gets its name from being naively based on Bayes' theorem, and making the assumption that all features are independent of each other. This naive assumption makes the calculation simpler. The core idea is that the presence or absence of a feature is unrelated to other features in the same class. For example, in identifying a fruit, the color is independent of the shape. While this independence assumption is often violated in reality, naive Bayes still performs surprisingly well on many classification tasks, especially with large datasets and many output classes. It calculates the conditional probability of each class, given the values of the features, using a simple mathematical formula derived from Bayes' theorem. Some of the key advantages of naive Bayes' algorithm are: simple to implement, handles high dimensions well, requires less training data, fast and highly scalable. Naive Bayes is commonly used in areas like text classification, spam filtering, recommendation systems and sentiment analysis, where the feature independence assumption is not overly violated. So, in simple terms, it's a probabilistic classifier that makes predictions by calculating conditional probabilities of classes given the feature values, while naively assuming all features are independent. And now, we will discuss about linear regression. Linear regression is a fundamental supervised learning algorithm used for predictive modeling and finding relationships between variables. The core idea is to plot the data points on a graph, with the x-axis representing the independent variables and the y-axis representing the dependent variable we want to predict. It then tries to find the best fitting straight line that models the linear relationship between the variables. This straight line is called the regression line. The regression line is chosen such that the sum of the squared distances between the actual data points and the points on the line is minimized. This allows making predictions for new data. Some of the key points to remember are that linear regression is used for predictive analytics and forecasting continuous numerical values. Models the relationship between one dependent variable and one or more independent variables. Simple and effective for linearly related data. Commonly used in many fields like finance, economics, marketing, etc. The algorithm learns from labeled training data to understand how the dependent variable changes in relation to changes in the independent variables. It identifies the optimal linear relationship or straight-line equation. This linear regression line can then be used to make predictions by plugging in new values for the independent variables. In essence, it is finding the straight line that best summarizes and models the linear patterns in the data for predictive purposes. The next topic in this course is logistic regression. Logistic regression is a type of supervised learning algorithm used for classification problems, especially when the output is binary, 0 or 1, yes or no. Unlike linear regression, which outputs continuous numerical values, logistic regression is used when the target variable is categorical, such as spam or not spam email, disease present or not, customer will buy or not buy. The core concept is to use the input independent variables to estimate the probability of the binary outcome being true, 1. It does this by fitting a special, logistic, S-shaped curve function to the data. This logistic function maps any input value to an output probability between 0 and 1. The algorithm learns the optimal logistic curve equation from the training data labeled with the correct 0 to 1 outcomes. The curve's coefficients determine how the input variables influence the probability predictions. So for any new data instance, logistic regression calculates the probability of it belonging to the 1 class based on the input variables and the learned logistic equation. Some of the key use cases of logistic regression include email spam detection, disease diagnosis predictions, marketing for likelihood of customer purchase, credit risk analysis. In simple terms, logistic regression estimates the probability of a binary event occurring, rather than predicting exact numerical values like linear regression. It achieves this via the logistic S-curve transformation. Now let us discuss about k-means clustering. The k-means algorithm is a clever tool that helps us group similar things together. It's like a sorting hat for data, working in the realm of unsupervised learning where it learns from the data without any prior guidance. This algorithm starts by taking all the data, regardless of its group, and plots it out. Then, it randomly selects a piece of data from each group and considers it as the center point, or the centroid. Imagine drawing a circle around each group with the centroid in the middle. The algorithm then sorts the remaining data points into their respective groups based on how close they are to the centroid. The k-means algorithm begins with an unlabeled dataset and divides it into a certain number of groups, or clusters. This number is represented by k and should be predetermined. The algorithm keeps repeating the process until it finds the best possible clusters. Here's how it works. Choose the number k to decide how many clusters you want. Randomly select k points or centroids. Assign each data point to the closest centroid, forming the predefined k clusters. Calculate the variance and place a new centroid for each cluster. Repeat the previous step, which means reassign each data point to the new closest centroid of each cluster. The algorithm keeps doing this until it thinks it has the best clusters possible. But remember, you have to tell the algorithm how many clusters you want at the beginning. Next, let's talk about Gaussian mixture model. GMM are quite similar to k-means clustering. Both aim to sort data into predetermined clusters based on how close the data points are to each other. However, GMM is a bit more flexible when it comes to the shapes of the clusters it can create. While k-means clustering only allows data to be grouped in circles with the centroid in the middle, GMM can handle data that forms more linear patterns. This means GMM can create oblong-shaped clusters, providing clearer groupings if a data point falls within the circle of another cluster. The starting point and training process of k-means and GMM are the same. However, they differ in their approach. K-means uses a distance-based approach, while GMM uses a probabilistic approach. GMM operates under one main assumption: the dataset is made up of multiple Gaussians, or in other words, a mixture of Gaussians. This makes it a great tool for tasks like forecasting product sales or understanding customer churn by looking at different groups of customers. It's also worth noting that some AI algorithms, like GMM, can work with either supervised or unsupervised data. This means they can have slightly different uses depending on the nature of the data they're working with. The next topic is k-nearest neighbor, KNN. The k-nearest neighbor algorithm is a straightforward AI algorithm that makes a simple assumption that all the data points provided are close to each other. It plots these points on a map to show their relationship. Once the data points are plotted, the KNN algorithm calculates the distance between them, which helps to understand the relationship between different data points. By calculating these distances and plotting them on a graph, the algorithm can provide a visual representation of how closely related different data points are. In other words, KNN is like a tool that helps us see how close different pieces of data are to each other, providing valuable insights into their relationships. Both supervised and unsupervised learning algorithms can benefit from the use of KNN algorithm. In supervised learning, KNN can be used for either classification or regression tasks. For instance, if we have a set of data points labeled as either category A or category B, we can use KNN to determine which category a new data point belongs to. In unsupervised learning, KNN is commonly used for anomaly detection. This means it can help identify data points that don't belong and remove them. This is particularly useful when dealing with large datasets where unusual data points can skew results. KNN is a nonparametric algorithm, which means it doesn't make any assumptions about the underlying data. This makes it a flexible tool that can be used in a variety of situations. It's also known as a lazy learner algorithm. Unlike other algorithms that learn from the training set immediately, KNN simply stores the dataset during the training phase. When it receives new data, it classifies this data into a category that is most similar to the new data. While KNN can be used for both regression and classification tasks, it is most commonly used for classification problems. For example, if we have two categories, category A and category B, and a new data point, x1, we can use KNN to determine which category this new data point belongs to. This makes KNN a valuable tool for identifying the category or class of a particular dataset. Next topic is neural networks. Neural networks are a collection of AI algorithms designed to mimic the functions of a human brain. They are more complex than many other AI algorithms, and their potential applications are still being explored. In both supervised and unsupervised learning, neural networks can be used for classification and pattern recognition. They consist of interconnected nodes, or neurons, organized into layers. Information flows through these nodes, and the network adjusts the connection strengths, or weights, during training to learn from data. This enables it to recognize patterns, make predictions, and solve various tasks in machine learning and artificial intelligence. The architecture of a neural network typically includes three layers: the input layer, the hidden layer, and the output layer. The hidden layer, of which there can be more than one, is sometimes referred to as a distillation layer. This is because it extracts the most relevant patterns from the inputs and sends them on to the next layer for further analysis. By recognizing only the most important information from the inputs and discarding redundant information, neural networks can accelerate and improve the efficiency of the learning process. Due to their ability to learn and adapt, neural networks are a powerful tool in the field of AI, capable of tackling complex tasks and providing valuable insights. Let's discuss reinforcement learning algorithms. The last major type of AI algorithm is reinforcement learning algorithms, which learns by taking in feedback from the result of its action. This is typically in the form of a reward. A reinforcement algorithm is usually composed of two major parts. An agent that performs an action, and the environment in which the action is performed. The cycle begins when the environment sends a state signal to the agent. That cues the agent to perform a specific action within the environment. Once the action is performed, the environment sends a reward signal to the agent, informing it on what happened, so the agent can update and evaluate its last action. Then, with that new information, it can take the action again. That cycle repeats until the environment sends a termination signal. There are two types of reinforcement the algorithm can use, either a positive reward, or a negative one. In reinforcement algorithms, there are slightly different approaches depending on what is being measured and how it's being measured. Here are some definitions of different models and measures. Policy, the approach the agent takes to determine the next action taken by the agent. Model, the situation and dynamics of the environment. Value, the expected long-term results. This is different from the reward, which is the result of a single action within the environment. The value is the long-term result of many actions. Value-based. In a value-based reinforcement algorithm, the agent pushes toward an expected long-term return, instead of just focusing on the short-term reward. Policy-based. A policy-based reinforcement algorithm usually takes one of two approaches to determining the next course of action. Either a standardized approach where any state produces the same action, or a dynamic approach where certain probabilities are mapped out and probabilities calculated. Each probability has its own policy reaction. Model-based. In this algorithm, the programmer creates a different dynamic for each environment. That way, when the agent is put into each different model, it learns to perform consistently under each condition. In January 2017, the U.S. Public Policy Council of the Association for Computing Machinery, ACM, which consists of educators, researchers, and professionals in the world of information technology, outlined a set of guiding principles that could serve as a precursor for an algorithmic Bill of Rights. These principles cover 7 general areas, which we will be discussing one by one. Awareness: those who design, implement, and use algorithms must be aware of their potential biases and possible harm, and take these into account in their practices. Access and redress: those who are negatively affected by algorithms must have systems that enable them to question the decisions and seek redress. Accountability: organizations that use algorithms must take responsibility for the decisions those algorithms reach, even if it is not feasible to explain how the algorithms arrive at those decisions. Explanation: those affected by algorithms should be given explanations of the decisions and the procedures that generated them. Data provenance: those who design and use algorithms should maintain records on the data used to train the algorithms and make those records available to appropriate individuals to be studied for possible biases. Auditability: algorithms and data should be recorded so that they can be audited in cases of possible harm. Validation and testing: organizations that use algorithms should test them regularly for bias and make the results publicly available. In this course we covered some of the popular algorithms like decision trees, random forests, support vector machines, naive Bayes, linear and logistic regression, k-means clustering, Gaussian mixture models, k-nearest neighbors, and neural networks. It also discusses the Algorithmic Bill of Rights, which outlines principles for the ethical use of algorithms. Also, we would request you to stay tuned to our channel for updates and new content on AI algorithms and their applications in marketing and other industries. Don't forget to subscribe to our channel to receive notifications about new videos.